So in the last video we took a very long-winded way of finding the Taylor series, or the Taylor polynomials for e to the x and sine of x. And what we noticed when we did that process was we found a pattern that we can use on any function, not just sine and e to the x. And so what we found is called a Taylor series generated by our function at x equals 0. So when it's centered at x equals 0, it's technically called the Maclaurin series, which is just, I guess, another mathematician who was interested in Taylor in series centered at 0. We're going to see that we don't have to center them at 0. We can center them at any x value we want. But the definition is, if f is a function with derivatives of all orders, it just means that you can keep taking derivatives with this function throughout some open interval containing 0, then the Taylor series generated by f at x equals 0 is given by what you see below. So a couple of things I want to point out. First of all, it's a series because it's a sum, and it's technically an infinite series because it's never ending. So there's a plus a dot 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 here at the end, meaning it's in theory you can keep going forever. The second thing is, I didn't put them in the first two terms, but I really could have to make the pattern clear. I could have put this as a 1 factorial and this is 0 factorial here. And so you can see that the degree of the polynomial, or I should say the degree of the term, and the factorial and the derivative all match up. So for instance, it's 1 factorial, the degree is 1, first derivative. Right? In general, it's the nth degree, n factorial is below, and it's the nth derivative. So that's an easy way to remember this pattern as you're building these. And the other thing is that this here, these first two terms, that's just the linearization, which is our fancy name for the tangent line. The linearization at x equals 0. So this, viewing it this way, it's almost as if the linearization is just a special case of this grand scheme, sort of a bigger idea of approximating functions using polynomials. So if you stop at degree 1, you're using the tangent line, which we've seen does a really good job of approximating the function. But you don't have to stop there. You can build polynomials that approximate your function to whatever degree you want. So this is a series. To be technical, if you decide to truncate this series anywhere, then you've constructed what's called a Taylor polynomial. So if we do what's called the partial sum, so the partial sum would just mean stop somewhere. So let's just say it's f of 0 plus f prime of 0 plus f prime of 0 times x plus f double prime of 0, x squared over 2 factorial. Let's just say you did it all the way up to the nth. Right, so notice this time I stopped. I'm not putting a dot 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 after that. Then this is the Taylor polynomial. It's a polynomial because polynomials end. They actually have a degree. This would have degree end. This is the Taylor polynomial. Of order n, or degree n, for f at x equals 0. So you can build a Taylor series, which goes on forever. It's kind of the almost like the DNA or thumbprint for your entire function. When you want to approximate the function using polynomials, then you'll use the partial sum, and you'll use whichever, depending on the degree of accuracy that you're after, you'll just use whatever degree polynomial you need. All right, so that's a Taylor polynomial of order n. So this is the definition of Taylor series generated f at x equals 0. So now that we have a formula, I want to actually find the fourth order Taylor polynomial that approximates y equals cosine of x near x equals 0. But I want to do it not using what we did in prior videos. I actually want to use the recipe. So I want to use the fact that a Taylor polynomial, what does it say? A fourth order. So I'm going to use this notation. The fourth order Taylor polynomial is just going to be f of 0 let's just be really thorough, x to the 0 over 0 factorial plus f prime of 0, x divided by 1 factorial plus f double prime of 0, x squared over 2 factorial plus the third derivative at 0, x cubed over 3 factorial plus the fourth derivative. So notice the method's different now. We're using the recipe that we stumbled upon doing it the long way before. So now all we need to do, we've got our function cosine of x. We just need to find f of 0, f prime of 0. We got to find these guys and then plug them in. So f of x is cosine, f prime of x is going to be negative sine, f double prime of x would be negative cosine, f triple prime be positive sine, and then the fourth degree would be cosine again. And so that tells us that f of 0 is 1, f prime of 0 is 0, f double prime of 0 is negative 1, f triple prime of 0 is 0, and the fourth derivative is 1. So let's just make those substitutions. So I'm going to take this, and this, and replace them, or replace what they are up there. So we get f of 0 is 1, so it's just 1, x to the 0 times 0 divided by 0 factorial. F prime of 0 is just a 0, so that goes away. I'm just going to write it in for now. We'll write everything in now, I guess. F double prime of 0 is negative 1. F triple prime of 0 is 0. And the fourth derivative at 0 is 1. So when you simplify everything, you end up getting, in the end, that the fourth degree Taylor polynomial for cosine is just going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. So that's our Taylor polynomial, and then the next thing we're asked to do is find the Taylor series for cosine of x in sigma notation. So you can probably see that for cosine, it looks like there's a nice pattern emerging here. And in fact, if I could write this 1 as x to the 0 over 0 factorial, and you can really see that the pattern's pretty obvious, right? So the next term is probably going to be minus x to the 6th over 6 factorial, and then plus x to the 8th over 8 factorial. So what we say is that the Taylor series for cosine is, and watch what I do here, I'm actually writing a strict equal sign, not approximately equal to, it's strictly equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. I'm going to put negative 1 to the n, I guess, depending on what we call n, x to the 2n over 2n factorial. And now if we wanted to write that in sigma notation, just as some practice for sigma notation, right? Sigma notation is useful for describing a sum. So what we'd want to put inside is our general rule. So our general rule is it's like negative 1 to the n, x to the 2n, divided by 2n factorial. And now we just want to make sure our indices start. So our indice is going to go up to infinity, right? Because this series will never end. We want our indice to start in such a way that the first output is a 1. So I think that means I need to put a 0 here. And that would make the first output a 1. When you plug in a 1, you'll get negative x squared over 2 factorial. So this is working for us. So there is the Taylor series. This is the Taylor series for cosine. And what I'm going to do on the next page is just give you the Taylor series for cosine, for sine, and for e to the x, because those are ones you'll want to memorize, especially if you're taking an AP calculus course. Those are the ones you'd be expected to memorize rather than rederiving all the time. So here are the Taylor series for e to the x, sine of x, and cosine of x. Again, these would be worth memorizing because they're going to come up a lot. The nice thing about having some of these main Taylor series memorized is you can make new ones pretty painlessly. So for instance, we know that cosine of x, its Taylor series is going to be, or the fourth order Taylor polynomial, let's write that, is going to be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. Right? Fourth order, fourth degree. So what's really nice is we can treat these almost like we can treat these exactly like functions where the cosine of x is equal to what we see above. Therefore, the cosine of 3x would be 1 minus, rather than x squared, 3x squared over 2 factorial. Rather than x to the fourth, 3x to the fourth over 4 factorial. So it becomes very easy to make make some new functions using some transformations, and the Taylor series just transform in the way you'd expect them to. And so therefore, for using very little effort, I now have a fourth order Taylor polynomial for cosine of 3x centered at x equals 0. So if I were to graph this polynomial, you'd expect it to look to conform to cosine of 3x as long as you're near x equals 0. There are other ways you can transform them, so let's look at sine of x and try to see if we can find out a Taylor series for x sine of x. So this time we want a Taylor series, not a polynomial. So that means we're not stopping this Taylor series. We need it to continue forever. So we know sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, right, all the way up to negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So if I want to make the Taylor series for x sine of x, you just need to treat this like an equation, times both sides by x. And you can literally distribute that x to every single term, including the general term, and you'll get that x sine of x can be written as, so x times x is x squared, minus x to the 4th over 3 factorial, plus x to the 6th over 5 factorial, minus x to the 8th over 7 factorial. So you see what's happening. It's just bumping the degrees up. So in the general term, if you want to bump this degree up, you just write x to the 2n plus 2 divided by 2n plus 1 factorial. This is a useful skill. Make sure you're able to do this, because it's what I find is a lot of students go back to that recipe, the f of 0 plus f prime of 0, which sometimes you have to do, but you don't have to do it for functions whose Taylor series you know by heart, such as sine of x, cosine of x, and e to the x. So you never want to redo work that you don't need to do. So memorizing sine of x and cosine of x and e to the x, later on in the course you'll memorize 1 over 1 minus x. You need to memorize those so that you're not doing more work than you have to.